124 light-years from Earth, a telescope just caught a whisper of something that should not exist without life. The James Webb Space Telescope locked onto a planet called K2-18b, and inside its atmosphere, it found a molecule that, on our world, only living oceans produce. We are about to travel to a sun the color of dying embers, sink into a sea wider than any continent, and stand inside the strangest alien sky humanity has ever measured. If wonder still moves you, take a second to like and subscribe. Now hold your breath. We begin. The signal arrived as a tiny dip in starlight, barely a flicker against the cosmic dark. Astronomers in a control room at the Space Telescope Science Institute in Baltimore stared at the readout for a long moment before anyone spoke. The James Webb Space Telescope had just finished one of the most ambitious observations of its young career, pointed for hours at a single faint star burning quietly in the constellation Leo. That star, called K2-18, has a planet circling it. And that planet had just told us a secret. The dip itself looked unremarkable. To an untrained eye, it would have seemed like noise, a wobble in the data, the kind of nothing that gets discarded 1,000 times a day. But astronomers know how to read these flickers. When a planet crosses in front of its star, a sliver of starlight passes through the planet's atmosphere on its way to us. That light gets bitten by molecules. Each gas leaves a unique mark, a missing color in the spectrum, a wavelength stolen mid-flight. The pattern of what is missing tells you what the air is made of. For months, a team led by Cambridge astrophysicist Niku Madhusudan worked through the data. They cleaned it, modeled it, tested it against rival explanations. Then a wavelength signature emerged that none of them had truly expected to see. It belonged to a molecule called dimethyl sulfide. On Earth, dimethyl sulfide has a single known origin. It comes from the oceans. More specifically, it comes from microscopic plankton, the kind of life that drifts in the upper layers of seawater and gives the coast that briny smell after a storm. The team checked the signal again. They ran the analysis through a different instrument on Webb. The fingerprint stayed. They estimated the concentration in K2-18b's atmosphere to be more than 10 parts per million, thousands of times stronger than anything found in Earth's air. That number alone should have been impossible. On a sterile planet, sunlight should rip a molecule like that apart in a matter of years. To find it floating in such abundance, something has to be making it, constantly, faster than it can be destroyed. Madhusudan's team did not announce the discovery of life. They were careful about that. The result reached what scientists call a 3 sigma confidence level, meaning there is a roughly 1 in 300 chance the signal is a coincidence. To formally claim a discovery, astronomers want 5 sigma, where the odds of a fluke drop to less than 1 in 3 million. K2-18b is not there yet, but it is closer than anything humanity has ever measured before. What makes the moment different is the weight of context. K2-18b is the right size, in the right zone, around the right kind of star, with an atmosphere already known to contain methane and carbon dioxide. Now, possibly, a gas that on our planet has never been produced by anything except living organisms. Add it all up, and you get a target unlike any other in the known universe. The whisper from 124 light-years away may turn out to be a misreading, a chemical trick, an instrument quirk, or it may be the first time another world has answered us back. Before we ask which, we need to understand the molecule itself, and that part of the story begins underwater. If you have ever stood near the ocean and breathed in that sharp, slightly sweet smell after a wave breaks, you have inhaled the molecule at the heart of this mystery. Dimethyl sulfide is what gives the seaside its scent. It rises from the surface of every ocean on Earth, and when you trace it back to its source, you arrive at the smallest creatures in the food chain. Phytoplankton, single-celled organisms that drift through sunlit seawater in numbers beyond counting, manufacture the gas as a byproduct of their daily survival. The chemistry is simple. These tiny living things produce a compound called dimethyl sulfoniopropanate inside their cells. It helps them regulate pressure and resist the salt of the ocean. When the cells are damaged, eaten, or die, that compound breaks down and releases dimethyl sulfide into the water. From there, it bubbles up into the air. Earth's atmosphere holds the molecule at concentrations below 1 part per billion, a trace so faint that detecting it from another planet should be physically impossible. Yet here is the strange part. In every laboratory test ever run, in every chemical pathway scientists have mapped, dimethyl sulfide on Earth has only one origin story. Volcanoes do not make it. Lightning does not make it. Comet impacts do not make it. Burning rock does not make it. The only known producer is biology, living things. That is why, for decades, astronomers have placed the molecule near the top of a short and sacred list. The list of biosignature gases, compounds whose presence in an alien atmosphere would suggest, with very few alternatives, that something there is alive. This is what makes the K2-18b detection so unsettling. The signal Webb captured is not a hint, not a faint suggestion. The estimated abundance sits at over 10 parts per million. To put that in perspective, you would need to multiply Earth's natural level by roughly 10,000 to reach what is floating around K2-18b. Imagine walking outside and finding the air around you 1,000 times more salty, 1,000 times more humid, 1,000 times more thick with the smell of the sea. That is the scale of what the telescope appears to have found. A skeptic might ask whether some unknown chemistry could create the same gas without life. That is a fair question, and scientists are pursuing it aggressively. So far, every laboratory attempt to produce dimethyl sulfide in significant quantities through pure chemistry has failed. Sunlight breaks the molecule down within years. To maintain such a concentration, something must be replenishing the supply at an enormous rate. On Earth, the rate matches the activity of the global plankton population. On K2-18b, whatever is producing it would have to be working even harder. There is also a sister molecule in the data, dimethyl disulfide, almost identical in structure, also turned up in the same wavelength range. On Earth, this one too points back to microbes. Both gases tend to appear together when biology is involved, like fingerprints left at the same scene by the same hand. The pattern alone does not prove anything, but it tightens the noose. To explain it without life, you would need a chemical reaction nobody has ever observed, in conditions nobody has ever modeled, which raises the next question. What kind of world is K2-18b? K2-18b does not look like Earth, Mars, or anything sitting in our solar system. It belongs to a category of worlds astronomers have only recently dared to imagine and only barely begun to find. The category has a name, Hycean. The word stitches together two ideas, hydrogen and ocean, and it describes exactly what the theorists believe: a planet wrapped in a thick blanket of hydrogen gas, with a single global sea churning beneath it. Picture a world larger than Earth, but smaller than Neptune. K2-18b is about 2.5 times wider than our planet and roughly 8.5 times more massive. That puts it in the awkward middle. Too big to be a rocky terrestrial world, too small to be a gas giant. For a long time, planets like this were assumed to be miniature versions of Neptune, cold balls of crushing pressure with no surface to speak of. Then the modeling changed. A team of theorists, including Madhusudhan himself, began to ask what would happen if such a planet sat closer to its star, where the temperature was mild enough for water to remain liquid. The answer they got was startling. Under the right conditions, the hydrogen atmosphere could act like a greenhouse cap, trapping heat and allowing a deep ocean to exist beneath, not a small one. An ocean that would cover the entire planet, edge to edge, with no continents, no islands, nothing breaking the surface. A world that is, from horizon to horizon, water. The numbers behind this idea are dramatic. The ocean on a Hycean world might run hundreds of miles deep, far deeper than any sea on Earth. The deepest trench on our planet, the Mariana, drops about 7 miles. On K2-18b, the seafloor could lie 50 times farther down. The pressure at the bottom would be staggering, but the water near the surface might sit at temperatures that, by ocean standards, look almost familiar, warm, possibly even hot, maybe close to the temperature of a hot bath. This is the model that makes the dimethyl sulfide signal so explosive. If you take Earth's biology and ask what it would do on such a world, the answer is straightforward. Plankton-like organisms would thrive in the upper, sunlit layers of the ocean, exactly as they do here. They would absorb light, exchange gases with the atmosphere, and as they lived and died, release sulfur compounds into the air above. The Cambridge team's calculations show that a global Hycean ocean teeming with that kind of microscopic life would produce dimethyl sulfide at roughly the abundance Webb appears to have detected. It fits suspiciously well, some say. Skeptics warn that the Hycean model itself is still a hypothesis, not a confirmed fact. The planet's true structure remains uncertain. Some researchers argue K2-18b might instead be a magma world, with a molten rocky surface beneath its atmosphere, or even a gas-dominated planet with no surface at all. The dimethyl sulfide signal, if real, would bend strongly toward the ocean version. But the data is not yet airtight. What is undeniable is that we are looking at a place that, by every available measurement, sits inside its star's habitable zone. The water can be liquid there, the chemistry allows life, and the telescope keeps pulling stranger things from the atmosphere. To understand why this single planet became the prime target, we need to go back to the moment astronomers nearly missed it. K2-18b was not always famous. For most of its known existence, the planet was little more than a number in a database, one entry among thousands of candidates flagged by a wounded space telescope on its second life. The discovery happened in 2015, almost by accident. The Kepler Space Telescope, the most successful planet hunter in history, had broken. 2 of its 4 reaction wheels had failed, leaving it unable to hold its gaze steady. NASA engineers improvised a fix, repurposing the dying spacecraft for a new mission called K2. The telescope would now stare at different patches of sky for shorter windows, watching for the same telltale flickers as before. In one of those windows, a star in Leo gave a small dimming pulse every 33 days. The pattern repeated, clean and predictable, the kind of regular rhythm that screams orbiting body. Astronomers logged it. The planet got its name from the project and its position in the catalogue, K2-18b, a neat label for a world that, at the time, looked utterly unremarkable. For nearly a decade after, K2-18b sat in scientific obscurity. It was too far away for direct imaging, too small to be a giant, too oddly sized to fit cleanly into any existing model. Most of the planetary science community in the late 2010s was still focused on rocky planets, the Earth analogues, the hot Jupiters bright enough to study. K2-18b fell into the in-between, a so-called sub-Neptune. There were thousands of those by then, and most were dismissed as uninteresting, too big to be habitable, too gassy to walk on. The first crack in that assumption came in 2019. Astronomers using the Hubble Space Telescope and an older instrument called Spitzer reported water vapor in the atmosphere of K2-18b. It was the first time water had been detected on a world inside its star's habitable zone. The result made headlines for a week, and then the story largely faded. Hubble's data was thin, the signal was contested, and no one could say for sure whether the water was abundant or fleeting. What changed everything was the launch of the James Webb Space Telescope. From its first months of operation in 2022, Webb began rewriting what was possible. The instrument is so sensitive, so precisely tuned to infrared wavelengths, that it can pull chemical signatures out of starlight with a clarity Hubble could only dream of. When the Cambridge team requested time on Webb to revisit K2-18b, they were not chasing a long shot. They had a hunch the older Hubble result was real, and they wanted to know what else might be hiding in that atmosphere. In September 2023, the first Webb observations came back. Methane, carbon dioxide, both gases at clear, confident levels. It was the first time carbon-bearing molecules had ever been spotted in a habitable zone exoplanet's air. That alone should have been a milestone, but buried in the same data, in a noisier corner of the spectrum, was a faint smudge that hinted at something else. The team reported it cautiously. They did not yet trust it. That smudge was the first whisper of dimethyl sulfide. It was not strong enough to be a result, but it was strong enough to demand a second look. The team applied for more telescope time. They aimed Webb's most sensitive infrared instrument at the planet again, and then the signal grew. To understand what is happening on K2-18b, you have to look up at its sky. The sun hanging there is nothing like ours. K2-18 is what astronomers call a red dwarf, a small, cool, slow-burning star, roughly half the mass of our own sun and far less luminous. From the surface of K2-18b, if you could stand on a surface, the star would not look small. Because the planet orbits far closer than Earth does to the sun, the disk of K2-18 would loom large in the sky, perhaps twice the apparent size of our solar disk, glowing a deep, sullen orange-red. Red dwarfs are the most common stars in the galaxy. Roughly 7 out of every 10 stars in the Milky Way belong to this category. They are also strange. They burn cooler than yellow stars, with surface temperatures around 5,000 degrees Fahrenheit compared to the sun's 10,000. They live longer too. A red dwarf can keep burning hydrogen for hundreds of billions of years, while our sun has a total lifespan closer to 10 billion. If life emerges around a red dwarf, it has an almost unimaginable amount of time to evolve. But there is a violent side to these stars, and it complicates the story. Red dwarfs are notorious for stellar flares. They can erupt with bursts of radiation many times stronger than anything our sun produces, and they do it often, sometimes several times a day during their younger phases. Each flare blasts the inner planets with a wave of high-energy particles and ultraviolet light. On a world without a strong magnetic field, that radiation can strip the atmosphere away over millions of years. It can sterilize the surface. It can shred molecules like dimethyl sulfide on contact. K2-18 is, fortunately, an older red dwarf. Estimates put its age in the multi-billion-year range, well past the most violent flaring period of its youth. The planet has likely had time to settle into a stable state, but the radiation environment is still harsher than anything Earth deals with. Whatever atmosphere K2-18b has managed to keep must be either replenishing constantly or shielded by something. That shielding may come from the atmosphere's own thickness. Hydrogen blankets are heavy and tall. The gas envelope on K2-18b is thought to extend many thousands of miles above the planet's possible ocean surface. As starlight enters that envelope, it gets scattered, absorbed, and softened by the time it reaches the lower layers. By the time the red glow filters down to where life might exist, it would be dim, ruddy, and far less hostile. The same hydrogen that makes K2-18b strange also makes it survivable. There is another quirk. Red dwarfs put out most of their energy in red and infrared wavelengths. That means any photosynthesis happening on K2-18b, if life exists, would not produce green leaves the way Earth plants do. It would tune itself to longer wavelengths, possibly producing pigments closer to deep purple, brown, or black. An alien plankton bloom in K2-18b's ocean might paint the sea a color that, to a human eye, would look almost like dried blood. Standing on a hypothetical raft above that ocean, the experience would be alien beyond imagination. A low red sun, a boiling sky, a sea the color of rust, and somewhere in the water below, possibly, the source of the molecule that pulled humanity's attention across 124 light-years of empty space. The James Webb Space Telescope cannot see K2-18b directly. The planet is a dim point of warmth lost in the glare of its star, billions of times brighter, and from 124 light-years away, no telescope humanity has ever built can split them apart. So, how exactly did we measure the air of a world we cannot even resolve as a pixel? The answer is a technique called transit spectroscopy. It works by patience and geometry. As K2-18b orbits its star, there comes a moment, every 33 days, when the planet passes directly between the star and Earth. From our vantage point, the planet briefly crosses the face of its sun. The starlight dims by a tiny fraction, less than half of 1%, and during that dimming, something extraordinary happens. A thin sliver of starlight grazes the edge of the planet. It passes through whatever atmosphere is there, and it carries with it a record of every molecule it touched. That sliver of light is what Webb is built to read. The telescope's instruments split incoming light into its component colors, the way a prism breaks sunlight into a rainbow, but with hundreds of times more precision. Each molecule absorbs specific wavelengths, the way a thumbprint leaves a unique mark. Water absorbs in one band, methane in another, carbon dioxide elsewhere. Dimethyl sulfide has its own distinct fingerprint, a cluster of features in the mid-infrared region that show up only if the molecule is there. To get a clean signal, astronomers need many transits. The dimming caused by a planet's atmosphere is so faint that a single observation drowns in noise. Webb has watched K2-18b cross its star multiple times, stacking the data from each transit on top of the others. The pattern that emerges, slowly, is a spectrum, a graph of which wavelengths went missing during the planet's passage. Read it correctly, and you have a chemical inventory of the air. For K2-18b, two of Webb's instruments did the heavy lifting. The first was NIRSpec, the near-infrared spectrograph, which captured the methane and carbon dioxide back in 2023 and gave the first hint of dimethyl sulfide. The second was MIRI, the mid-infrared instrument, which observed the planet again in 2024 and sharpened the signal in a different wavelength range. When the two instruments agreed on the dimethyl sulfide feature, the scientific weight of the result jumped considerably. Two independent looks, two different chemical bands, the same answer. The technique has limits. Transit spectroscopy only samples the upper atmosphere, the region where starlight grazes the planet's edge. It cannot tell you what is happening deep below the clouds. It cannot tell you the temperature at the surface, only the pressure and chemistry of the high gas layers. It also cannot resolve where on the planet the gas is concentrated. The signal Webb gets is an average across the entire dayside terminator, a ring around the planet where day meets night. This is why scientists keep insisting the result is not a final answer. The data tells us something is in the atmosphere, in significant quantities, with a chemical fingerprint that matches a biosignature gas. It does not tell us where. It does not tell us what is making it. It does not tell us, yet, whether something is alive down there. To get closer, the team needs more transits. And the next layer of the puzzle is what happened in 2023. Before dimethyl sulfide, there was carbon. In September 2023, the Cambridge team published their first major Webb result on K2-18b, and the headline was simpler but no less stunning. They had detected methane and carbon dioxide in the planet's atmosphere, both at clear, statistically strong levels. It was the first time in the history of astronomy that carbon-bearing molecules had been confirmed in the air of an exoplanet sitting inside its star's habitable zone. That sentence sounds technical, but the meaning is huge. Methane and carbon dioxide are the building blocks of carbon chemistry, the same chemistry that underpins every form of life we know. Detecting them on a temperate world is a precondition for asking the bigger question. Without carbon, the conversation about life is over before it starts. With carbon, in the right ratios, the conversation has just begun. The amounts mattered too. The Webb data showed methane and carbon dioxide present at roughly 1% abundance in K2-18b's atmosphere. That number is consistent with what theorists predicted for a Hycean world. On a planet covered by a global ocean, water would dissolve much of the available carbon dioxide and lock it away in the sea. The leftover atmospheric concentration should fall in the range Webb actually measured. It was a quiet but powerful piece of confirmation. The planet, on first chemical inspection, looked exactly like the model said it should. There was something else hiding in the same data, or rather, something not hiding: ammonia. On a planet with a thick hydrogen atmosphere and no ocean, ammonia should form readily and accumulate to detectable levels. Webb found almost none. The absence was striking. It suggested that ammonia was being removed from the atmosphere somehow, and the most natural explanation was that it was dissolving into a vast body of liquid water below. A world without an ocean would hold on to its ammonia. A world with one would scrub it from the air. So, in a single observation, the team had gathered 3 independent chemical clues. Methane was present, carbon dioxide was present, ammonia was missing. Each line of evidence on its own would be interesting. Together, they painted a coherent picture: a temperate planet, with carbon chemistry intact, with its atmosphere actively interacting with a deep liquid reservoir below. The Hycean hypothesis went from a theoretical curiosity to a working model with real numerical support. In the same September 2023 paper, almost as a footnote, the team noted a tentative additional signal. There was a small bump in the spectrum at a wavelength known to be associated with sulfur compounds. The signal was weak. The statistical confidence was low. The team could not say with any certainty that they had detected dimethyl sulfide. They flagged it, published the caveat, and asked for more telescope time. That single caveat changed the trajectory of the entire project. Within months, Webb was scheduled to observe K2-18b again, this time with the MIRI instrument, optimized for exactly the wavelength range where the dimethyl sulfide signature was suspected. The observation took 8 hours. The data took weeks to process, and when the results finally arrived in early 2025, the faint smudge from 2023 had become something the team could no longer dismiss. The methane and the carbon dioxide had set the stage, but the chemistry of K2-18b's atmosphere was about to get much, much stranger. Sometimes the most important discovery is something that is not there. For K2-18b, the absence of a single molecule may be just as telling as everything Webb did detect. That molecule is ammonia, and the way it has gone missing tells us something profound about what lies beneath the planet's clouds. Ammonia is a simple compound, 1 nitrogen atom bonded to 3 hydrogens. In a hydrogen-rich atmosphere like the one wrapping K2-18b, ammonia should form naturally and abundantly. Nitrogen is one of the most common elements in the universe. It bonds eagerly with hydrogen at the temperatures and pressures expected in such an environment. Every model of a sub-Neptune planet predicts that ammonia should be a major component of the atmosphere, often hovering in the percent range. On K2-18b, theorists expected it to show up loud and clear. It did not. When the Cambridge team analyzed the Webb spectrum, they found ammonia at levels far below predictions. The molecule's fingerprint, which should have been one of the most prominent features in the data, was almost invisible. Something was removing it from the air at an extraordinary rate. The question was what? The leading explanation comes from the chemistry of seawater. Ammonia is highly soluble in water. Pour it into a cup, and it dissolves instantly. On a planet with a thick global ocean, atmospheric ammonia would constantly rain down, dissolve into the upper layers of the sea, and disappear from view. The atmosphere above would be left almost stripped of the molecule. exactly as Webb observed. In other words, the missing ammonia is a signature of a hidden ocean. This is a different kind of evidence than the dimethyl sulfide signal. It does not depend on any biological process. It does not require life. It only requires liquid water in vast quantities in contact with the lower atmosphere. The fact that ammonia is gone is telling us, with high confidence, that something down there is absorbing it, and the most natural absorber, by an enormous margin, is an ocean. Combine this clue with the methane and carbon dioxide measurements, and the picture sharpens further. Methane is present, but not at the runaway levels predicted for a planet with a magma surface. Carbon dioxide is present in exactly the proportion expected if a surface ocean is dissolving the rest. Ammonia is gone, in a way that makes sense only if there is liquid water below. 3 independent chemical measurements, all converging on the same conclusion. K218b has an ocean. That conclusion alone, if it holds, would be one of the most important scientific findings of the century. A confirmed ocean on a planet beyond our solar system, sitting in the habitable zone of its star, with carbon-based chemistry in the atmosphere above. Even without dimethyl sulfide, the world would be a target worth devoting decades to. The dimethyl sulfide signal, layered on top of the ocean clues, is what pushed the story past mere habitability into the territory of biosignatures. It is one thing to find a place where life could exist. It is another to find a place where the air smells like life is already there, and the smell, faint as it is across 124 light-years of space, has been growing more distinct with each new observation. The next step was to look at the molecule's fingerprint up close, which meant turning to a new set of eyes. When the Cambridge team requested follow-up observations of K218b, they specifically asked for time with one instrument on the James Webb Space Telescope, not the one that had given them the methane and carbon dioxide. A different one, designed for a different range of light, and far better suited to chasing the molecule they suspected was hiding in the data. The instrument is called MIRI, the Mid-Infrared Instrument, and it became the key that unlocked the next stage of the K218b story. To understand why MIRI matters, you have to think about how molecules absorb light. Every gas has its own preferred wavelengths, the way every voice has its own tone. Some molecules sing in the visible range, others in the ultraviolet, others in the near-infrared just past red, and others in the deeper mid-infrared, where heat itself glows. Dimethyl sulfide and dimethyl disulfide both have their strongest absorption features in the mid-infrared region, between roughly 6 and 11 microns of wavelength. That range is exactly where MIRI is built to look. The previous Webb observations of K218b had used NIRSpec, an instrument tuned to near-infrared light. It was sensitive enough to spot methane, carbon dioxide, and a faint hint of something sulfurous in 2023. But it was not optimized for the wavelengths where dimethyl sulfide shines brightest. Asking NIRSpec to confirm the molecule was like asking a pair of binoculars to read a license plate 2 miles away. You might catch a smudge, you won't get the letters. MIRI is a different beast. It is cooled to cryogenic temperatures, just a few degrees above absolute zero, to keep its own heat from contaminating its observations. It uses an entirely separate set of detectors and optics, optimized for wavelengths up to 28 microns. When MIRI looks at a transit spectrum, it pulls out chemical features that other instruments would smear into noise. For a molecule like dimethyl sulfide, MIRI is the right tool. The team scheduled an 8-hour observation. Webb stared at K2-18 as the planet crossed the face of its star, capturing the slim crescent of starlight that filtered through the atmosphere. The data flowed back to Earth and into the hands of analysts at Cambridge and the Space Telescope Science Institute. They processed it through multiple independent pipelines, each using different software and assumptions to make sure the result was not an artifact of one method. The signal held in the wavelength range where dimethyl sulfide was expected, the spectrum showed a clear absorption feature. Dimethyl disulfide, the related molecule, also appeared in the same region. Both fingerprints were present, both stronger than any plausible noise floor. The team ran simulations of what the spectrum should look like if the molecules were absent. Those simulations did not match the data. The simulations that included dimethyl sulfide and dimethyl disulfide did. This is where the 3 sigma confidence level came from. After all the analysis, all the cross-checks, all the independent pipelines, the chance that the signal was random noise stood at roughly 1 in 300, not bulletproof, but strong enough to publish, strong enough to make the entire field of exoplanet science sit up and start arguing. The arguing began almost immediately, because while the signal was real, the question of what made the signal was wide open, and the abundance the team estimated turned out to be the most provocative number of all. The number that made the room go quiet was 10 parts per million. That was the abundance the Cambridge team estimated for dimethyl sulfide in the atmosphere of K218b. 10 molecules of the gas for every million molecules of air. To anyone outside the field, that sounds tiny. To an exoplanet astronomer, it sounds impossible. Here is the comparison that matters. On Earth, the atmospheric concentration of dimethyl sulfide hovers below 1 part per billion. That is 1 molecule per billion molecules of air, a trace so faint you could not detect it from across the room with any chemical sensor. Multiply Earth's concentration by 10,000, and you arrive at what Webb seems to be seeing on K218b. Whatever is producing the gas, there is producing it at a rate that dwarfs Earth's entire global ocean output. To understand what that means physically, consider how the molecule behaves once it enters an atmosphere. Dimethyl sulfide is fragile. Ultraviolet light from any star, even a cool red dwarf, breaks the molecule apart in a matter of years. Without continuous replenishment, the gas would vanish from the atmosphere on a timescale far shorter than the age of the planet. For Webb to detect 10 parts per million, something on K218b must be releasing dimethyl sulfide into the air faster than sunlight can destroy it, continuously. At a planetary scale, Earth's plankton produce roughly 20 million metric tons of dimethyl sulfide per year. That output keeps Earth's atmospheric concentration at the parts per billion level. To sustain 10 parts per million on a planet with K218b's volume and gravity, the production rate would need to be vastly higher. Estimates from atmospheric models suggest the source on K218b would have to outpace Earth's entire planktonic output by a factor of hundreds, possibly thousands. Whatever is making this gas, it is not a small operation. It is filling the sky. Skeptics have raised the obvious question: could a non-biological process generate that much dimethyl sulfide? Several teams have run laboratory experiments and computer simulations to test the idea. Some recent work, including a NASA-led study published in 2025, suggests that under certain extreme conditions, photochemistry, the action of starlight on simpler molecules, could produce dimethyl sulfide abiotically. The catch is that the conditions required are unusual, the production rates are uncertain, and the model predictions do not yet match the abundance Webb actually measured. The math, in other words, is tight. If the abundance estimate from the Cambridge team holds up under further observation, the abiotic explanations have to work very hard to keep up. If the abundance is somehow lower than estimated, perhaps the team overinterpreted noise, then chemistry has more room. The next round of Webb observations, between 16 and 24 additional hours of telescope time, should pin the number down with much greater precision. There is also the matter of dimethyl disulfide. The Webb data suggests both molecules are present together in the same wavelength region at comparable abundances. On Earth, biology produces both gases in tandem, often in roughly the proportions Webb appears to be measuring. To replicate that pairing through pure chemistry would require not just one new abiotic pathway, but two, working in coordinated balance. The closer you look at the numbers, the harder they are to explain without invoking something living. But astronomy has been fooled before, and the field's own caution has good reason to exist. In physics and astronomy, certainty has a number. The number is sigma, written as the Greek letter, and it measures how confident a result is. A 1 sigma signal is barely there, the kind of bump in the data that could easily be random noise. A 3 sigma signal is much stronger, with roughly a 1 in 300 chance of being a coincidence. A 5 sigma signal is the gold standard. At 5 sigma, the odds of the result being a fluke drop to less than 1 in 3 million. In particle physics, you do not announce a discovery until you cross 5 sigma. That is the line. The dimethyl sulfide detection on K2-18b sits at 3 sigma. That is why the Cambridge team, careful and disciplined, refuses to call it a discovery of life. They have called it the strongest evidence yet of a possible biosignature. They have called it a hint, a candidate, a starting point. They have not called it proof. The distinction is not modesty. It is the iron rule of how science protects itself from its own enthusiasm. History is the teacher here. Astronomy has been burned by 3 sigma results before. In 2020, a team announced the detection of phosphine in the clouds of Venus, framing it as a possible sign of microbial life floating in the planet's upper atmosphere. The result hit 3 sigma, generated worldwide headlines, and within months was challenged by independent reanalysis. Several follow-up studies failed to reproduce the signal. Today, the phosphine claim remains contested, and most planetary scientists treat it with deep skepticism. The lesson stuck. There are many ways a 3 sigma signal can dissolve. The data could have been processed with a model that biased the result. The instrument could have a subtle quirk that mimics the molecule's fingerprint. The star itself could be variable in ways that produce false absorption features. Even the way the planet's atmosphere is layered, with cloud decks, hazes, and altitude-dependent chemistry, can fool atmospheric retrieval algorithms into reporting molecules that are not really there. Any of these factors could be at play on K2-18b. To climb from 3 sigma to 5 sigma, the Cambridge team needs more telescope time. They have estimated that between 16 and 24 additional hours of Webb observation focused on K2-18b's transits would push the statistical confidence past the threshold. That request has been submitted. The Webb Time Allocation Committee, which decides how the most expensive telescope ever built spends its limited hours, treats every request rigorously. Approval is not guaranteed. But the scientific case is strong. The community wants the answer. Even 5 sigma would not, by itself, prove life. It would prove that the molecule is really there, with extraordinarily high statistical confidence. It would not prove that biology made it. To get to that conclusion, the field needs to rule out every plausible, non-biological source, and that work is happening in parallel. Laboratory experiments, atmospheric models, reanalyses of Webb data with different assumptions. Each piece chips away at the uncertainty. The team on the ground has been remarkably restrained about the result. Madhusudan himself has said, repeatedly, that his role is to be deeply skeptical of his own findings. That is how science has to work. Get excited, then test again. Believe the result only when it survives every reasonable attempt to break it. The first attempts to break it have already begun, and some of them have hit hard. Within days of the Cambridge team's April 2025 announcement, the response from the rest of the exoplanet community arrived. Some of it was congratulatory, most of it was cautious, and a few critiques landed with the force of a hammer. The most prominent came from Jake Taylor, an astronomer at the University of Oxford, who specializes in exactly the kind of atmospheric retrieval the Cambridge team had performed on K2-18b. Taylor took the publicly available Webb data and ran his own reanalysis. His method was simple, well-established, and used a different statistical approach. He called it a flatline test. The idea was to ask whether the K2-18 K2-18b spectrum could be explained without invoking any specific molecule at all. If you fit the data with a flat line, no features, no absorption, no chemistry, how poorly does that fit work? If the fit is bad, then the data must contain real signals, and the work of identifying which molecules they are can proceed. If the fit is acceptable, then the case for any specific molecule weakens substantially. Taylor ran the numbers and found something uncomfortable. The Webb data on K2-18b in his analysis was consistent with a flat line. That did not mean the original team was wrong. It meant that the signal, at the level of statistical confidence currently available, was not strong enough to rule out the simplest possible explanation. Noise, a non-detection, a spectrum that, within its error bars, contained no detectable molecular features at all. His conclusion was that more data was needed before any biosignature claim could be taken seriously. The signal, he argued, was too marginal. It depended too sensitively on how the analysis was set up. Change the assumptions slightly, and the dimethyl sulfide feature wavered. Hold the assumptions tight, and it appeared. That kind of fragility, Taylor warned, is not what a robust detection looks like. Other voices in the field echoed the concern. Laura Kreidberg, a leading exoplanet atmosphere researcher at the Max Planck Institute for Astronomy in Germany, said publicly that the strength of the evidence depended too heavily on the specific choices of analysis, and that those choices did not yet meet her bar for a convincing detection. Sarah Seeger, the MIT astronomer who helped pioneer the entire field of biosignature studies, said even more bluntly that the K2-18b finding would likely remain in the candidate category indefinitely, and that enthusiasm was outpacing evidence. These were not fringe critics. They were senior figures, deeply invested in the search for life beyond Earth, with no agenda except scientific rigor. Their warnings carried weight precisely because they wanted the result to be real and were unwilling to accept it on insufficient grounds. The Cambridge team responded with measured confidence. They acknowledged the critiques, defended their methodology, and pointed out that their analysis had used multiple independent pipelines that all returned consistent results. They did not back down from the 3 sigma claim. They did, however, agree that more telescope time was needed. The best way to settle the dispute, they said, was more data. The full Webb dataset became publicly available in late April 2025, exactly 1 year after collection. Other teams could now run their own analyses with their own methods and reach their own conclusions. The next several months produced a flood of papers, some supporting the original detection, some challenging it. The debate was just beginning. Then NASA stepped in. In July 2025, a team of researchers, led by scientists at NASA's Jet Propulsion Laboratory, uploaded a paper to the RxIV preprint server. The paper was a direct response to the Cambridge claim. It used the same Webb data on K2-18b. It applied different atmospheric models, different chemical assumptions, and a different framework for how light interacts with the planet's air. And it reached a strikingly different conclusion. The NASA-led analysis confirmed several of the Cambridge team's findings. Yes, K2-18b appears to have a complex atmosphere. Yes, the data is consistent with significant water content. Yes, the planet sits in its star's habitable zone, with chemistry that does not rule out an ocean below the clouds. On those points, the two teams agreed, but on the dimethyl sulfide signal, the new paper diverged sharply. The NASA group reported that they could not find conclusive evidence for the molecule in the data. With their modeling choices, the signal that had appeared at 3 sigma in the Cambridge analysis dropped below the threshold of statistical significance. Within their framework, the spectrum was ambiguous. More importantly, the NASA team made a second argument that struck at the heart of the biosignature claim. They ran detailed photochemical simulations of K2-18b's atmosphere, modeling how starlight interacts with various sulfur compounds in a hydrogen-rich environment. Their results showed that, under certain conditions, Abiotic processes could generate detectable levels of dimethyl sulfide and related organosulfur molecules. No life required. The chemistry alone, driven by ultraviolet light from the red dwarf star, could in principle produce the gas in observable quantities. This was a significant blow. It did not disprove the biosignature interpretation, but it broke the previously tight argument that dimethyl sulfide on K2-18b had to come from biology. If photochemistry could fake the signal, then even a confirmed 5 sigma detection of the molecule would not, by itself, be enough to claim life. The field would need additional evidence to rule out the abiotic pathway. The NASA paper's authors framed their work carefully. They were not arguing that K2-18b is sterile. They were arguing that the data, as currently available, does not require a biological explanation. The planet remains a remarkable target. The case for an ocean remains strong. The chemistry remains consistent with habitability. But the leap from interesting chemistry to actual life, they cautioned, was not yet supported by what Webb had measured. The Cambridge team responded with their own technical critiques. They argued that the photochemical models used by the NASA group made simplifying assumptions that may not apply to a real Hycean atmosphere. They pointed out that producing dimethyl sulfide abiotically at the rates needed to match observations was, in their view, still a stretch. The two teams agreed to disagree, publicly and politely, while both pushed for more telescope time to settle the question. What had started as a single dramatic claim had become a working scientific debate. Multiple teams, multiple analyses, multiple interpretations of the same dataset. From the outside, this can look messy. From the inside, it is exactly how science is supposed to work. A signal appears, a claim is made. Other groups challenge the claim with their own methods. Theories sharpen, models improve, and eventually, the truth emerges from the friction. But the question kept circling back. If life is the answer, what kind of life would even be possible down there? To imagine what might be alive on K2-18b, the most useful place to look is not space. It is your nearest beach. The dimethyl sulfide that fills the planet's possible atmosphere has, on Earth, a single dominant source: phytoplankton, microscopic organisms that drift through the upper layers of the world's oceans, carrying out photosynthesis, dying, getting eaten, and in the process producing the molecule that gives the sea its smell. Phytoplankton are not a single species. They are a vast category, including diatoms, dinoflagellates, cyanobacteria, and dozens of other groups. They are responsible for roughly half of all photosynthesis on Earth, producing about half the oxygen in the atmosphere. Without them, the planet would not be habitable for most of the life forms that exist today, including humans. Their role in the global carbon cycle, the sulfur cycle, and the climate system is so fundamental that scientists often describe them as the engine of the biosphere. The key chemical they produce, the one relevant to K2-18b, is dimethyl sulfoniopropanate, mercifully shortened to DMSP. Phytoplankton make DMSP inside their cells as a kind of biochemical multi-tool. It helps them regulate the salt and water balance against the surrounding seawater. It protects them against ultraviolet damage and oxidative stress. When the cell is damaged, eaten, or breaks down at the end of its life, enzymes convert the DMSP into dimethyl sulfide, which then escapes into the atmosphere. The amount produced is staggering. Earth's oceans release about 20 million metric tons of dimethyl sulfide every year. Most of it gets oxidized in the atmosphere within days, breaking down into sulfate aerosols that seed cloud formation and influence the planet's climate. Some scientists have proposed that phytoplankton, through this very process, help regulate Earth's temperature on geological timescales. Life and atmosphere locked into a feedback loop that has shaped our world for billions of years. If something like phytoplankton exists on K2-18b, the math becomes interesting. The planet is much larger than Earth, with a vastly bigger ocean surface area, a global Hycean sea, hundreds of miles deep and covering the entire planet would dwarf Earth's combined oceans by orders of magnitude. The total habitat available for plankton-like organisms would be enormous. To produce 10 parts per million of dimethyl sulfide in the atmosphere, the equivalent biomass would not need to do anything Earth's plankton do not already do. It would just need to do it in aggregate on a planetary scale. There is no reason in principle why such organisms could not exist. They would need liquid water, which K2-18b appears to have. They would need carbon, which the methane and carbon dioxide measurements confirm is available. They would need sulfur, which the dimethyl sulfide signal itself implies is present. They would need an energy source, and the red dwarf star above provides plenty of light, especially in the infrared range that life could potentially harness with the right photosynthetic pigments. What such organisms would actually look like is impossible to know. They might be single-celled, like Earth's plankton. They might be more complex. They might use biochemistry that is broadly similar to Earth's, or radically different. They might float in the upper sunlit layers of the ocean, or live in chemical gradients deeper down, near the seafloor. Whatever they are, if they are there at all, they are living under conditions that no Earth organism has ever experienced. K2-18b is too big to be Earth. That single fact has shaped the entire scientific debate around it. The planet is roughly 2.5 times wider than our world and about 8.5 times more massive. On any chart of known exoplanets, it falls into a category that sits awkwardly between two well-defined classes. It is not a rocky terrestrial world like Earth, Venus, or Mars. It is not a gas giant like Jupiter or Saturn. It belongs to the strange middle ground that astronomers call sub-Neptunes, a class of planets that does not exist in our solar system at all. The size matters because it determines what the planet is made of. Gravity scales with mass, and on K2-18b, the surface gravity, if there is a surface, would be about 1.5 times what you experience on Earth. A person who weighs 150 pounds at home would weigh roughly 220 pounds on K2-18b. That increased gravity has consequences for how the atmosphere behaves, how dense it gets, and how thick the gas envelope around the planet can grow. Density is the giveaway. Astronomers can calculate the average density of a planet if they know its mass and its radius. Both are measurable for K2-18b. The mass comes from the wobble it induces in its parent star as it orbits. The radius comes from how much starlight it blocks during transits. Plug both numbers in, and you get an average density of roughly 2.5 grams per cubic centimeter. That is much less dense than Earth, which sits at about 5.5. It is also too dense to be a pure gas planet. K2-18b cannot be entirely rock, and it cannot be entirely gas. It must be something in between. The leading interpretations split into 3 main possibilities. The first is the Hessian model, a rocky core, a deep global ocean of liquid water, and a thick hydrogen atmosphere on top. The second is the so-called gas dwarf model, a rocky core and a very deep, very hot hydrogen and helium atmosphere, with no surface ocean at all, just a smooth transition from gas to compressed fluid as you descend. The third is the magma ocean model, a rocky core covered by a sea of molten rock, hot enough to glow, with a hydrogen atmosphere above sustained by volcanic outgassing. Each model produces different chemistry in the upper atmosphere. The Hessian model predicts the methane, carbon dioxide, and missing ammonia that Webb actually measured. The gas dwarf model predicts more ammonia and a very different sulfur chemistry. The magma ocean model predicts much higher temperatures and a wholly different mix of trace gases. Of the 3, only the Hessian model fits all of Webb's measurements simultaneously. That is why the Cambridge team has favored it. The chemistry pulls them in that direction. Skeptics caution that the planet's interior is not directly observable. We are inferring it from atmospheric measurements, which can be ambiguous. There may be other configurations of mass and composition that produce the same observed spectrum. Some researchers have argued that K2-18b could be a magma world with an atmosphere that mimics Hycean chemistry, or a gas dwarf with unusual photochemistry. These alternatives are minority views, but they are not zero. The size problem, in the end, is not a problem. It is the source of the planet's strangeness, and the reason its conditions might allow something Earth cannot. If K2-18b really has a deep ocean, the world beneath those hydrogen clouds is a place of crushing extremes. The pressure at the surface of any Hycean ocean would be far higher than at sea level on Earth. The atmosphere itself, dense with hydrogen and helium, presses down with the weight of thousands of miles of gas above it. By the time you reach the air-water boundary, the pressure could be hundreds, possibly thousands, of times Earth's atmospheric pressure. Standing there would be impossible for any human. The atmosphere alone would crush a body before you could blink. Beneath the surface, the situation gets more extreme. An ocean hundreds of miles deep would generate pressure at the bottom that no Earth submarine could survive. For comparison, the deepest point in Earth's oceans, the Mariana Trench, sits about 7 miles below sea level. The pressure there is more than 1,000 times atmospheric, roughly 16,000 pounds per square inch. Earth's deep-sea submersibles have to be built like spheres of solid titanium just to survive a single dive. On K2-18b, a similar craft would need to handle pressures 50 times greater. The bottom of a Hycean ocean is, by any human standard, a place of unthinkable force. What does this mean for life? On Earth, the deep sea is not lifeless. Far from it. Bacteria, fish, and even larger animals thrive at pressures we once thought fatal. Hydrothermal vents on the ocean floor host entire ecosystems built around chemical energy from the planet's interior, with no sunlight at all. Tube worms, vent shrimp, and exotic microbes live in scalding water laced with sulfides and metals, in conditions that would kill almost anything from the surface. The lesson is clear. Life on Earth has colonized every pressure regime we can reach, including some we thought were uninhabitable. If K2-18b is a Hycean world, the most interesting layer for life is probably not the bottom, it is the top. The upper few miles of the ocean, where light still penetrates, where temperatures remain moderate, where the chemistry is most active. This is where Earth's plankton live, and it is where any analogous organism on K2-18b would most likely flourish. Below that photic zone, the ocean would grow darker, colder, and denser. Life could persist there, perhaps, but it would have to draw its energy from chemistry rather than light. The temperature profile inside the ocean is its own puzzle. Models suggest that the surface waters of K2-18b's ocean could be quite warm, possibly above the boiling point of water at Earth pressure, but kept liquid by the enormous overlying atmosphere. As you descend, the temperature might rise further due to the planet's internal heat, eventually reaching a layer where the water transitions into a strange, high-pressure phase that does not exist on Earth's surface. Some researchers think the deep ocean of a Hycean world could include exotic forms of ice, called supionic or high-pressure ices, that remain solid even at scorching temperatures. If this is accurate, K2-18b's ocean is not a single uniform body of water. It is a layered structure, with warm liquid on top, transitional phases below, and exotic high-pressure ice, forming a kind of seafloor where rock would normally be. Life, if it exists, would be confined to the upper layers, floating in conditions both familiar and utterly alien. The dimethyl sulfide in the air, then, is the breath of that floating life. Nobody has measured the surface temperature of K2-18b directly. Every estimate published so far is a model output, a calculation based on the planet's distance from its star, its atmospheric composition, and assumptions about how heat flows through the system. The numbers vary widely depending on which assumptions you accept, and the question of whether the surface is warm enough for liquid water remains, even now, one of the most contested aspects of the entire discovery. The starting point is straightforward. K2-18b receives roughly the same amount of stellar energy per square mile as Earth does from the Sunday. Its orbit places it at the inner edge of what astronomers call the habitable zone of its red dwarf star, the region where liquid water could, in principle, exist on a planetary surface. That is the basic reason K2-18b became a target in the first place. The energy budget allows for water to remain liquid, given the right atmospheric conditions. The complication is the atmosphere itself. Hydrogen is a powerful greenhouse gas, but it works differently than the carbon dioxide and water vapor that dominate Earth's greenhouse effect. A thick hydrogen envelope traps heat efficiently, raising surface temperatures well above what stellar energy alone would predict. Some High-Scion models put the surface of K2-18b's ocean at temperatures comparable to a tropical sea on Earth, perhaps in the range of 70 to 100 degrees Fahrenheit. Other models, with different assumptions about atmospheric thickness and cloud cover, push the surface temperature much higher, into ranges that approach or exceed the boiling point of water at sea level. Why does this matter? Because life, as we understand it, requires liquid water within a specific temperature range. Most Earth organisms function between roughly 32 and 150 degrees Fahrenheit. Beyond that range, proteins denature, membranes break down, and biochemistry stops working. There are extremophiles on Earth, microbes that survive in scalding hot springs at temperatures up to about 250 degrees Fahrenheit, but even they have hard upper limits. If K2-18b's ocean surface is hotter than that, no Earth-like life could survive there. Some recent atmospheric models have raised exactly this concern. Critics of the High-Scion interpretation have pointed out that the radiative balance on a planet with K2-18b's atmospheric composition might run hotter than the original Cambridge models assumed. If the surface is, say, 300 or 400 degrees Fahrenheit, the ocean could still exist in liquid form thanks to high atmospheric pressure, but the conditions for life become much more restrictive. Photosynthesis would still work in principle, but the molecular machinery of any living organism would have to be radically different from Earth's. The Cambridge team has defended their temperature estimates by pointing to the consistency of multiple chemical signals. Methane and carbon dioxide at the observed levels suggest a moderate temperature regime. The absence of ammonia suggests a cold enough lower atmosphere for the gas to dissolve into water rather than stay airborne. The sulfur chemistry, including the dimethyl sulfide itself, suggests organic processes rather than high-temperature decomposition. Each line of evidence supports a relatively temperate interpretation. The truth is that we will not know for certain until we get more data. Webb cannot directly measure surface temperature on a world wrapped in hydrogen clouds. The only path forward is more careful spectroscopy, more transits, more detailed atmospheric modeling. Each new observation tightens the bounds. While astronomers debate the temperature, another constraint is shaping the planet's environment in a way that Earth has never experienced. The way K2-18b spins. Every planet that orbits close to a small, cool star eventually faces the same fate. The gravity of the star tugs on the planet's bulges. Friction inside the planet drains rotational energy. Over millions of years, the spin slows, and finally settles into a rhythm where one face of the planet always points toward the star, and the other never does. Astronomers call this tidal locking. Our own moon does it to Earth, which is why we always see the same lunar face from the ground. K2-18b almost certainly does it to its star. The consequences are dramatic. On a tidally locked world, there is no day-night cycle the way Earth has one. There is no sunrise. There is no sunset. The star simply hangs in the sky over one hemisphere, fixed in place, burning red and unmoving for the entire age of the planet. The other hemisphere lives in permanent darkness, a night that has lasted billions of years and will continue for billions more. This creates a planet of permanent extremes. The day side, baked continuously by stellar radiation, becomes the hottest region. Heat builds up in the atmosphere directly beneath the star, with no cooling reprieve. The night side, by contrast, receives no direct light at all. Without the constant warmth of the star, temperatures there could drop sharply. Whatever heat the night side retains comes from atmospheric circulation, the constant flow of hot gas from the day side curling around the planet and shedding warmth into the dark. For a Hycean world like K2-18b, the tidal lock raises immediate questions about whether the ocean could remain liquid everywhere. On a thinner atmosphere, the night side could in principle freeze solid, leaving an ocean only on the day side and a vast hemisphere of ice on the other. The hydrogen envelope, however, changes the picture. A thick atmosphere transports heat efficiently. Wind patterns on K2-18b would likely run at extreme speeds, possibly thousands of miles per hour, dragging warm air from the substellar point around to the night side and back. The result could be a planet where the temperature difference between day and night is far smaller than you might expect. Models of similar tidally locked worlds suggest that, on a planet with a deep atmosphere, the day side and night side might differ by only a few dozen degrees rather than hundreds. The ocean could remain liquid across the entire surface, top to bottom, even on the side that never sees the star. That is not guaranteed. The exact behavior depends on atmospheric thickness, cloud distribution, and ocean circulation, all of which remain uncertain. What is certain is that life on a tidally locked world would face a strange spatial geography. The day side would be a permanent furnace, with the star always overhead. The night side would be a permanent darkness. Neither region, by itself, looks ideal for the kind of life Earth has produced. The day side might be too hot, the night side too dark. But there is a third region, a ring around the planet where day meets night, where the star sits forever on the horizon, never rising and never setting. This ring is called the Terminator, and of all the places on K2-18b, it may be the one most suited to life as we understand it. A permanent twilight zone with stable temperatures, available light, and conditions that change only with depth and weather rather than with day or season. That ring is where biology might gather, and the next chapter asks why. On a tidally locked planet, the Terminator is the boundary between eternal day and eternal night. It runs as a great circle around the entire world, dividing the burning hemisphere from the frozen one. From the perspective of an observer standing within it, the star would hover on the horizon, never moving, casting long red shadows across whatever surface stretched away into the distance. The light would be perpetual but soft, filtered through a thicker slice of atmosphere than reaches the substellar point. The temperature would sit between the dayside extreme and the nightside chill, often in a range that looks comparatively gentle. For decades, astronomers and astrobiologists have argued that the Terminator zone is the most promising habitat on any tidally locked exoplanet. The reasoning is straightforward. The day side is too hot. The night side is too dark. The Terminator gets enough light to drive photosynthesis, especially the kind that uses red and infrared wavelengths from a cool star, while avoiding the worst thermal extremes. On a Hycean world like K2-18b, this logic carries directly into the ocean. The Terminator ring would mark a band where the upper layers of the sea receive constant, stable illumination from a star that never moves. Imagine standing on a small platform in the middle of that ring, suspended above the surface of the ocean. The star K2-18 hangs at the horizon, half above and half below, frozen in place. To your left, the world brightens gradually toward day. To your right, it darkens toward eternal night. Behind you and ahead of you, the ring continues, all the way around the planet, a permanent dawn or dusk, depending on which way you face. The water below glows a deep red where the starlight strikes it. Plankton, if they exist, would gather in this band, their pigments tuned to drink the long wavelength light their star pours out. Atmospheric circulation on tidally locked planets tends to drive powerful jet streams along the terminator. Strong winds blow continuously, transferring heat from day to night. Storm systems may form along the boundary, raising mist and clouds that blur the line between hemispheres. On Earth, weather is driven mostly by the day-night cycle and by latitudinal temperature differences. On K2-18b, the analogous driver would be the substellar to antistellar gradient. The terminator becomes the equator of weather. The ocean below the terminator would also experience unusual currents. With one side of the planet permanently hotter than the other, surface waters would flow constantly from day to night, sinking in the cool regions, rising in the warm ones. The result is a kind of global conveyor belt, more steady than Earth's seasonal currents. Driven by the unchanging geometry of tidal lock, nutrients would mix continuously through the upper layers, creating ideal conditions for biological productivity in the very band where light is strongest. If life on K2-18b produces dimethyl sulfide, it most likely produces it here, in the terminator ring. The molecule rises into the atmosphere, gets carried by the planet-wide winds, and over time mixes throughout the entire upper air column. Webb, scanning the planet's atmosphere during transit, would not be able to localize the signal to the terminator specifically. The instrument averages over the whole limb of the planet, but the source, in the most plausible biological scenario, would be a band of ocean where conditions for life are most favorable. The terminator is not just a line on a map, it is a habitat, and it may be the best one in the visible universe. Stand on a raft at the surface of K2-18b's ocean, somewhere along the terminator, and let your eyes adjust to the strangeness. The sky is not blue. Hydrogen does not scatter light the way nitrogen does. The atmosphere overhead would have a deep orange or salmon hue, shading toward red as you look toward the star, and toward black as you turn toward the antistellar darkness. There would be no clouds in the Earth sense. There might be hazes, droplets of methane or sulfur compounds suspended high in the atmosphere, casting shifting bands of color across the sky. The star itself dominates the horizon. K2-18 appears about twice as wide as our Sun does from Earth, a swollen red disk that gives off a glow more like a forge than a daylight sky. The light is gentler than Earth's noon sunlight, but suffused with deeper warmth in the longer wavelengths. Your skin, under that light, would feel a slow heat, less sharp than Earth's sunshine but more pervasive, soaking through anything translucent. Visible details on the star, including spots, flares, and bright regions, would be dramatic features in the sky, shifting subtly as the star rotates over weeks. The ocean stretches in every direction. There are no continents on K2-18b, no islands, no coastline. The surface of the water is unbroken from horizon to horizon, a single global sea wider and deeper than any Earth ocean. Waves would still exist, driven by the same wind patterns that circulate heat from day to night. Some of those waves, on a planet with stronger winds and lower gravity at the upper atmosphere, could reach extraordinary heights. Imagine swells dozens of feet tall, rolling slowly under reddish light, reflecting the star in a long, shimmering streak across the water. The color of the sea itself is hard to predict. Water is naturally blue under sun-like light because it absorbs red wavelengths first. Under K2-18's red light, the water would absorb differently, possibly appearing gray, brown, or even purple. If photosynthetic organisms tinted the surface, the color might shift further. Earth's oceans look greenish in regions of heavy phytoplankton bloom. On K2-18b, the equivalent organisms could use pigments tuned to red and infrared light, possibly turning the upper waters dark crimson, deep brown, or the color of dried blood. The exact shade is unknowable. The general impression would be dim, ruddy, and utterly unlike Earth's blue Pacific. The smell, if you could remove your atmospheric helmet without dying, would be pungent, Dimethyl sulfide is what gives Earth's coast its briny scent, and on K218b, the gas would be present in concentrations thousands of times stronger. The air would reek of sea, intensified beyond anything coastal Earth produces, layered over the high-pressure thickness of hydrogen. Of course, you could not actually breathe the atmosphere. It contains almost no oxygen. A few seconds of unprotected exposure would suffocate you. The hydrogen might also be flammable in contact with any spark or heat source. Sounds would carry differently in such a thick atmosphere. Hydrogen transmits sound faster than nitrogen, and the higher density would amplify low frequencies. The crash of waves on no shore, the rush of wind, the rumble of distant atmospheric storms, all would feel deeper and more present than Earth's familiar audio environment. It is the most exotic setting biology has ever been suggested to inhabit, and it is 124 light-years away. For every piece of evidence supporting the biosignature interpretation of K218b, there is a counter-question waiting to be raised. One of the sharpest comes from a missing molecule, not the missing ammonia, which fits the Hycean ocean model. A different gas, ethane, whose absence is harder to explain if dimethyl sulfide is really there in the abundance Webb suggests. The chemistry is well understood. When a sulfur compound like dimethyl sulfide sits in the upper atmosphere of a planet illuminated by ultraviolet light, the molecule does not last long. Photons rip it apart, breaking the carbon-sulfur bonds. The fragments recombine into other compounds. One of the most predictable products of this process, given the carbon and hydrogen left over, is ethane. A simple molecule, two carbons bonded with hydrogens around them, easy to detect in infrared spectroscopy. If dimethyl sulfide is being continuously produced and continuously destroyed on K218b, ethane should accumulate as a byproduct. The expected concentration depends on the production rate of the parent molecule, but for 10 parts per million of dimethyl sulfide being processed by the star's ultraviolet output, ethane should appear at detectable levels. Specifically, the amount predicted by photochemical models would be high enough that Webb's MIRI instrument would see it clearly. Webb did not see it. The ethane signal in the K218b spectrum is at best weak. Some analyses suggest there is no detectable ethane at all. This is a problem for the biosignature interpretation. One of the most prominent voices to raise the concern was Edward Schwieterman, an astrobiologist at the University of California, Riverside, who has worked extensively on biosignature gases. He pointed out that the absence of ethane is unexpected if dimethyl sulfide is really present at the abundance the Cambridge team estimated. Either the photochemistry is being misunderstood, or the dimethyl sulfide is not really there in the amount claimed, or some unknown process is destroying ethane as fast as it forms. Each of those alternatives is uncomfortable. Misunderstood photochemistry is possible. The atmospheric models used to predict ethane production rest on assumptions about ultraviolet flux from K2-18, atmospheric mixing, and reaction rates that may not all be accurate. A revised model might allow for less ethane than originally expected, but the discrepancy is large enough that significant model revisions would be needed. The second possibility, that dimethyl sulfide is overestimated, is exactly what some skeptics have argued. If the true abundance is closer to 1 part per million rather than 10, the photochemical byproducts shrink correspondingly, and the missing ethane becomes less of a puzzle. But this interpretation also weakens the biosignature claim, since the lower the abundance of dimethyl sulfide, the less it stands out as a signature of life. The third option, an unknown ethane sink, would require some unidentified process actively removing ethane from the atmosphere as fast as photochemistry produces it. No such process has been proposed. It would be ad hoc, invoked specifically to rescue the original interpretation, which is exactly the kind of move scientists try to avoid. The ethane problem is not fatal to the biosignature claim. It is, however, a serious thread that needs to be pulled. The next round of Webb observations should give better constraints on both the dimethyl sulfide abundance and the ethane upper limit. If ethane stays missing while dimethyl sulfide stays strong, the puzzle deepens. The pressure to solve it is intense, because something even harder follows. K2-18b sits 124 light-years from Earth. That distance, written so casually, is almost incomprehensible at human scale. Light, which crosses our entire solar system from the Sun to Pluto in about 5 hours, takes 124 years to make the journey from K2-18b to here. A photon leaving the planet's atmosphere today will not reach Earth until the year 2150. The light Webb just analyzed left K2-18b in 1901, while the Wright brothers were still building their first glider, and the Titanic was a decade from launching. In miles, the distance comes to roughly 725 trillion. That is a 7, a 2, a 5, and 12 zeros. Putting it in driving terms is meaningless, but consider this. The fastest spacecraft humanity has ever built is the Parker Solar Probe, which during its closest approaches to the Sun reaches speeds of about 430,000 miles per hour. At that speed, a journey to K2-18b would take roughly 190,000 years. That is far longer than the entire history of modern humans on Earth. No conceivable propulsion technology, even on paper, could shorten that journey to anything resembling a human lifetime. Nuclear fusion drives, ion engines, theoretical antimatter rockets, all top out at velocities far below the speed of light. Even at 10% of light speed, a top-end goal for advanced propulsion concepts, the trip would take more than 1,200 years one way. We will not be sending a probe to K2-18b, not in this century, not in the next several centuries, possibly never. This is what makes Webb's observations so precious. The telescope is, in effect, the only way humanity will ever collect data from this planet. We cannot fly there. We cannot send a robot. We cannot drop a buoy into the ocean and listen for swimming things. Every fact we will ever know about K2-18b will arrive as photons captured by space telescopes, processed through analysis pipelines, debated in scientific journals, and synthesized into models. That is the entire toolkit. That is all there will ever be. The implications run deep. Even if Webb confirms the dimethyl sulfide signal at 5 sigma, even if follow-up observations rule out every plausible abiotic explanation, even if the entire scientific community converges on the conclusion that life must exist on K2-18b, no human will ever set foot there. No microscope will ever sample its plankton. No DNA, or whatever the alien equivalent might be, will ever be extracted, sequenced, and compared to Earth's biology. The discovery, if it happens, will remain forever distant, knowable only through chemistry inferred from starlight. That distance also shapes how the discovery, if confirmed, would land in human culture. There would be no expedition to organize, no mission to fund, no flag to plant. The result would be philosophical and scientific, not exploratory. Humanity would simply know, with high confidence, that we are not alone. And then we would have to live with that knowledge, applied to a place we will never visit. The light from K2-18b is still arriving. Every transit Webb captures is fresh information, decades old by the time it reaches us, but new to our understanding. The next decade of observations will refine the picture. Beyond that, larger telescopes will take over. But the original detection came from a small team that bet years of their careers on this one planet. Niku Madhusudhan grew up in India, studied physics at the Indian Institute of Technology, and earned his doctorate at the Massachusetts Institute of Technology. By the time he arrived at the University of Cambridge to lead his own research group, he had built a reputation as one of the most ambitious theorists in exoplanet atmospheres. His work was characterized by a willingness to propose new ideas, defend them through rigorous calculation, and follow them wherever the data led. He was the lead architect of the Hycean planet concept, the same model that has become central to interpreting K2-18b. Madhusudan's group at Cambridge's Institute of Astronomy bet heavily on K2-18b from the beginning. When James Webb began collecting science data in 2022, his team submitted observation proposals for the planet that were among the most detailed and well justified in the program. They argued that K2-18b sat at a unique intersection of conditions: the right size, the right orbital distance, the right kind of star, the right early atmospheric data from Hubble. The Webb Time Allocation Committee agreed and granted them observation slots. The work was not glamorous. Most of it took place in front of computer screens, processing terabytes of telescope data, running atmospheric models, debugging analysis pipelines, and arguing with collaborators about which assumptions to use. The team included researchers from Cambridge, the Space Telescope Science Institute in Baltimore, Cardiff University in Wales, and several other institutions. Names like Mons Holmberg, Subhajit Sarkar, and Savas Constantinou appear on the key papers, each contributing pieces of the puzzle. When the methane and carbon dioxide detection came back in September 2023, the team celebrated, but they also caught the faint hint of dimethyl sulfide in the same data. They could have published the methane and carbon dioxide alone and called it a major result. Instead, Madhusudan pushed to apply for more telescope time, specifically with the MIRI instrument, to chase the sulfur signal. The decision was not trivial. Webb time is precious. Asking for more, on the same planet, on a tentative signal, was a calculated risk. The risk paid off, at least to the level of 3 sigma. When the MIRI data arrived in early 2025 and the dimethyl sulfide feature held up across multiple analysis pipelines, the team prepared the publication carefully. Madhusudan was insistent, in meetings and in interviews, on framing the result conservatively. He repeatedly emphasized that the team was not claiming the discovery of life. They were claiming the strongest available evidence yet of a possible biosignature, which is a much narrower statement. When the paper was released in April 2025, the response was immediate and global. Press coverage exploded. Skeptical scientists pushed back. Independent reanalyses began within days. Madhusudan and his team weathered the criticism with patience, defending their methodology, acknowledging uncertainties, and continuing to ask for more telescope time to settle the question definitively. What is striking about the Cambridge team's approach is its discipline. Madhusudan has said publicly that scientists must be deeply skeptical of their own results, and he has practiced what he preaches. He has not declared victory. He has not claimed certainty. He has framed the K2-18b work as the beginning of a long process of investigation, not the end. That discipline is what science requires. It is also what makes the K2-18b story trustworthy, even amid the storm of debate. The team has earned its credibility through restraint. But astronomy has a long memory, and it remembers the false alarms. The K2-18b detection is not the first time astronomers have announced a possible biosignature. It is at least the third in recent memory, and the previous attempts offer cautionary tales that shape how the current claim is being received. To understand why the scientific community is treating K2-18b with such careful skepticism, you have to look at the ghosts of biosignatures past. The most famous example is phosphine on Venus. In 2020, a team led by Jane Greaves at Cardiff University announced the detection of phosphine gas in the upper atmosphere of Venus, framing it as a possible sign of microbial life floating in the planet's clouds. Phosphine, like dimethyl sulfide, is a molecule with no known abiotic production pathway in the Venusian environment. The detection was at roughly 3 sigma. The press response was enormous. Venus, the unloved sister of Earth, suddenly became a candidate for harboring life. Within months, the result began to crumble. Independent teams reanalyzed the same data and reported that the phosphine signal was much weaker than originally claimed, possibly non-existent. new observations using different telescopes failed to reproduce the detection. By 2022, the phosphine claim was widely regarded as either a misidentified spectral feature or a real but much smaller signal, well within the range of plausible non-biological explanations. The field had been burned. Today, very few astronomers consider phosphine on Venus to be evidence of anything other than the difficulty of doing this kind of measurement. A similar story played out earlier with methane on Mars. Multiple instruments, including ESA's Mars Express Orbiter and the Curiosity rover, have detected occasional bursts of methane in the Martian atmosphere. Methane, like dimethyl sulfide, can be produced by life, and the Martian detections were initially greeted with excitement. The challenge is that methane can also be produced by geological processes, including reactions between water and certain rocks. Years of follow-up observation have not resolved whether the Martian methane is biological or geological. It might be both. It might be neither. The signal exists, but its interpretation remains stuck. A third example is HCN hydrogen cyanide on the exoplanet GJ 1132b. Several years ago, an instrument suggested the presence of HCN in that planet's atmosphere, and the molecule was initially flagged as a possible prebiotic sign. Subsequent observations failed to confirm the detection at high confidence. The signal turned out to be marginal, dependent on specific analysis choices, and the interpretation never solidified. What ties these cases together is a common pattern. A team announces a biosignature detection at marginal statistical significance. The press amplifies the claim. Independent teams reanalyze and either fail to reproduce the signal or find that it can be explained without life. The original claim retreats into the contested literature, neither confirmed nor disproved, hanging in scientific limbo. K2-18b could go the same way, or it could be different. The key difference, so far, is the strength of the surrounding evidence. Methane and carbon dioxide are confirmed. The missing ammonia points to an ocean. Multiple instruments have caught the dimethyl sulfide feature. The case is broader than any previous biosignature claim, but broad does not mean confirmed. The history teaches caution. The Cambridge team knows this history better than anyone. Madhusudan was directly involved in some of the early debates over previous claims. He understands the trap. The plan to escape it is simple. Get more data? The question that hangs over K2-18b is not whether the dimethyl sulfide signal can be confirmed, it is when. The Cambridge team has estimated that between 16 and 24 additional hours of James Webb Space Telescope observation time, focused specifically on transits of K2-18b, would push the statistical significance from 3 sigma to 5 sigma. That is the threshold for what astronomers call discovery confidence. Crossing it would not prove life, but it would prove, beyond reasonable doubt, that the molecules are really there in the abundance claimed. Webb time is allocated through a competitive process. Every 6 months or so, scientists submit proposals describing what they want to observe and why. A panel of senior astronomers reviews the proposals and ranks them. Only a fraction are approved. The telescope is the most oversubscribed scientific instrument in human history, with proposal requests exceeding available time by factors of 5 or more in every cycle. Getting 16 additional hours on a single planet, especially one already heavily observed, requires a strong case. The case for K2-18b is, in fact, very strong. The scientific community broadly agrees that whatever the truth turns out to be, the question deserves a definitive answer. Either dimethyl sulfide is really there in the abundance the Cambridge team claims, in which case the implications for astrobiology are enormous, or it is not, in which case the field needs to know that too, in order to recalibrate its methods and avoid future false alarms. Either outcome is publishable, important, and worth telescope time. The follow-up observations would target the planet's transits with the MIRI instrument, the same one that produced the original dimethyl sulfide signal. The plan would be to stack additional transit spectra with the existing data, beating down the noise floor and sharpening the molecular features. With enough integration time, the signal-to-noise ratio improves to the point where statistical confidence rises to the discovery threshold. There is also the possibility that the additional observations will reveal something unexpected. Other sulfur compounds might appear. Other organic molecules might be detected. The atmospheric structure might turn out to be more complex than current models assume. Each new piece of information will help refine the interpretation regardless of whether the dimethyl sulfide claim survives. Beyond Webb, future telescopes will inherit the question. The next generation of space observatories, currently in design and planning stages, will be built with biosignature detection as a primary goal. The Habitable Worlds Observatory, a major NASA project slated for launch in the 2040s, will be specifically optimized to study exoplanet atmospheres at the level needed to confirm or rule out life. Ground-based extremely large telescopes, like the Extremely Large Telescope under construction in Chile, will also contribute through high-resolution spectroscopy of exoplanet light. By the time those instruments come online, K2-18b will have been observed for years, and the question of whether life exists there should be much closer to a definitive answer. For now, the field waits. The next round of Webb observations, if approved and executed, could come within the next year or two. The data analysis would take additional months. By the late 2020s, the K2-18b debate should be much further along than it is today. Either the signal will have been confirmed, or it will have been ruled out, or it will have been refined into something more nuanced than the original claim suggests. The patience required is not glamorous, but it is how the answer arrives. K2-18b is one planet. The galaxy contains hundreds of billions of stars, and current estimates suggest that nearly every one of them hosts at least one planet. That gives a rough total of trillions of planetary worlds in the Milky Way alone. Even restricting attention to planets in the habitable zones of their stars, the population is in the tens of billions. K2-18b is interesting precisely because it is the first to show a tantalizing biosignature, but it cannot remain unique for long. The James Webb Space Telescope is already pointed at other Hycean candidates. Several sub-Neptune planets in habitable zones around nearby red dwarf stars have been observed or are scheduled for observation. Their atmospheric chemistries are being characterized with the same techniques used on K2-18b. Some of these planets may turn out to have similar profiles, with methane, carbon dioxide, and possibly sulfur compounds in the air. Each new Hycean candidate is a chance to either confirm the pattern seen on K2-18b or to demonstrate that K2-18b is genuinely unusual. Beyond Webb, the next generation of telescopes is already being built. The Extremely Large Telescope, under construction on a mountain in northern Chile, will have a primary mirror more than 3 times wider than any existing telescope. When it begins science operations later this decade, it will be able to study exoplanet atmospheres with unprecedented resolution. It will not match Webb sensitivity in some wavelengths, but its ability to separate close pairs of stars and planets will allow direct imaging of some nearby exoplanets, a capability Webb largely lacks. The Habitable Worlds Observatory, a major NASA mission currently in planning, is being designed specifically to find and characterize Earth-like planets around Sun-like stars. The mission concept calls for a telescope larger than Webb, equipped with a coronagraph capable of blocking starlight to reveal faint planetary companions. By the 2040s, when the mission is expected to launch, it should be able to study the atmospheres of dozens of potentially habitable worlds at higher signal-to-noise than Webb can manage. Ground-based projects are also accelerating. The Giant Magellan Telescope and the 30-meter telescope, both planned for completion in the coming years, will join the extremely large telescope in providing massive collecting areas for high-resolution spectroscopy. Networks of smaller, specialized instruments are being deployed to monitor exoplanet transits continuously, looking for atmospheric variations and additional candidate worlds. The cumulative effect is that the search for biosignatures is shifting from the era of single hopeful targets to the era of statistical surveys. K2-18b will be joined by dozens, then hundreds, of similarly characterized worlds. The question of whether life exists elsewhere in the galaxy will be answered not by one dramatic detection, but by a growing body of atmospheric measurements, slowly painting a picture of how common or rare biological activity really is. There is friendly competition between teams. Different research groups have their favorite targets, their preferred instruments, their custom analysis pipelines. They publish papers rapidly, often within weeks of each other, building on and challenging one another's results. The pace of progress in the field has accelerated dramatically since Webb's launch in 2021. Where exoplanet atmospheric characterization once produced a few high-quality measurements per year, it now produces dozens. K2-18b helped trigger that acceleration. Whatever the final verdict on its biosignature signal turns out to be, the planet has already changed the field. It has shown what is possible. Other discoveries are coming. Before K2-18b became the most watched planet in the galaxy, the Haitian concept was a theoretical proposal with limited observational support. Now, with K2-18b as a worked example, astronomers are systematically searching for other planets that might fit the same profile. Several candidates have already been identified, and more are expected as Webb's mission continues. TOI 270D is one of the most discussed, discovered by NASA's TESS spacecraft and later observed with Webb. The planet sits in the habitable zone of a small red dwarf star about 73 light-years from Earth. Its size and mass place it in the sub-Neptune category, similar to K2-18b but slightly smaller. Webb observations of TOI 270D have detected both methane and carbon dioxide in its atmosphere, along with the same suspicious absence of ammonia that pointed to an ocean on K2-18b. The planet has not yet shown a clear dimethyl sulfide signal, but the underlying chemistry is consistent with a Haitian interpretation. LHS 1140b is another target getting serious attention. The planet orbits a small red dwarf about 40 light-years away, making it one of the closest sub-Neptunes in a habitable zone. Earlier observations with Hubble suggested water vapor in its atmosphere. Webb has been scheduled for follow-up observations to characterize the atmosphere in detail, with biosignature gases on the priority list. Results are expected within the next year or two. TRAPPIST-1 is a famous system that took the world by surprise when discovered in 2017. 7 Earth-sized planets orbit a small red dwarf about 40 light-years from Earth, with at least 3 of them sitting in the habitable zone. Webb has spent considerable time on the TRAPPIST-1 planets, looking for atmospheric signals. So far, the results have been mixed. Several of the planets appear to have very thin atmospheres or none at all, possibly stripped away by stellar flares. But TRAPPIST-1e, the most promising habitable zone candidate in the system, has not yet been ruled out as a biosignature target. Other candidates include K2-3d, GJ9827d, and several recently discovered sub-Neptunes from the TESS mission. Each one offers a different test of the Haitian hypothesis. Some are larger, some smaller, some hotter, some cooler. By comparing their atmospheric chemistries, astronomers can begin to map out which kinds of sub-Neptunes really do harbor oceans, and which are gas dwarfs without surfaces. The strategy is straightforward. Look for the same chemical fingerprints that made K2-18b interesting: methane, carbon dioxide, missing ammonia, possibly sulfur compounds. Planets that show the full pattern become high-priority biosignature targets. Planets that show only some of the markers go to the back of the line. There is also a deliberate search for planets that orbit cooler, longer-lived host stars. K2-18b orbits a fairly young red dwarf, which means its atmosphere has been exposed to relatively recent flare activity. Older red dwarfs, billions of years past their violent youth, might host planets with even more stable atmospheric conditions. Such planets, if they show Hycean chemistry, would be ideal targets for biosignature confirmation, since their atmospheric stability over geological time would make any detected molecules less likely to be transient anomalies. The field is just beginning. Within the next decade, the number of well-characterized sub-Neptune atmospheres should grow from a handful to dozens. Patterns will emerge. Some planets will look biological, some will look chemical, some will look ambiguous, like K2-18b itself. Whatever the eventual ratios, the search is producing a new kind of comparative planetology, one that includes alien biospheres as a possibility worth taking seriously. To understand why dimethyl sulfide matters, you have to understand how sulfur moves through a planet. On Earth, sulfur is an element that lives in many places at once. It sits inside rocks deep in the crust. It dissolves in seawater. It cycles through living organisms. It floats in the atmosphere as various gases and aerosols. And the rates at which it moves between these reservoirs are tightly tied to biology, geology, and climate. The sulfur cycle is one of the great planetary engines, alongside the carbon cycle and the water cycle. The biological side of the sulfur cycle on Earth runs largely through the oceans. Phytoplankton absorbs sulfate from seawater, incorporate it into proteins and other biomolecules, and as part of their metabolism, produce dimethyl sulfoniopropanate. When the cells are damaged or die, the compound breaks down and releases dimethyl sulfide, which then bubbles up into the atmosphere. There, the molecule is oxidized within days into sulfate aerosols, which seed cloud formation and eventually rain back to the surface. The cycle closes. On Earth, this cycle moves roughly 50 million metric tons of sulfur per year through the atmosphere. About half of that comes from biology. The other half comes from volcanic eruptions, ocean spray, and human industrial emissions. The biological contribution is the dominant signal in unindustrialized areas. Without phytoplankton, Earth's atmosphere would have far less dimethyl sulfide, fewer marine clouds, and a different climate. If K2-18b has a similar sulfur cycle driven by biology, the implications are profound. The planet's ocean would be a vast living sea, with organisms processing sulfur on a scale far beyond Earth's. The atmospheric concentrations Webb measured would be the steady-state output of a biosphere as productive as Earth's, perhaps more so. The dimethyl sulfide we detect from 124 light-years away would be the breath of an alien sea functioning, in chemical terms, much like our own. But the cycle could exist without life too. Sulfur is a common element. It comes out of volcanoes. It dissolves into oceans. It reacts with hydrogen, water, and carbon in ways that produce a wide variety of compounds. On a hydrogen-rich planet like K2-18b, the abiotic sulfur chemistry could in principle generate detectable amounts of various sulfur gases. Whether it can generate dimethyl sulfide specifically, at the abundance Webb detected, remains the contested question. Some recent work has shown that under specific conditions, ultraviolet light striking simpler sulfur compounds in a hydrogen atmosphere can produce small amounts of dimethyl sulfide as a photochemical byproduct. The rates are low, the conditions are specific. Whether they apply to K2-18b is uncertain. Most calculations suggest abiotic production cannot match the observed abundance. A few suggest it might, under generous assumptions about the planetary environment. The sulfur cycle on K2-18b if we could see it directly, would tell us almost everything we need to know. A purely abiotic cycle would be slower, more dependent on stellar inputs, and would produce different ratios of sulfur compounds than a biologically driven one. A living cycle would show patterns familiar from Earth, with biology dominating the gas exchange between ocean and air. Right now, we are seeing a single snapshot of the sulfur chemistry. The future observations will give us more. Over time, the picture will sharpen. Either K2-18b's sulfur cycle is dead chemistry, or it is alive. The molecules in its atmosphere are leaving fingerprints either way. The fingerprints have to come from somewhere. Even sterile worlds can be busy. Before assuming life on K2-18b, scientists are obligated to exhaust the alternatives. One of the most plausible non-biological explanations for the dimethyl sulfide signal is volcanism. Earth's volcanoes release a wide range of sulfur compounds, including hydrogen sulfide, sulfur dioxide, and trace amounts of more complex molecules. If K2-18b has volcanic activity below its possible ocean, similar processes could feed sulfur compounds into the atmosphere without requiring biology at all. The first question is whether K2-18b can have volcanoes. The planet's interior structure is uncertain, but most models include a rocky core surrounded by deep water. Volcanism on Earth is driven by heat from the planet's interior, including residual heat from formation and ongoing radioactive decay. K2-18b, being more massive than Earth, would retain more internal heat. It is therefore reasonable to expect that the rocky core would be active, with magma chambers, hydrothermal systems, and possibly underwater volcanic eruptions analogous to those on Earth's seafloor. Earth's mid-ocean ridges and hydrothermal vents do not directly produce dimethyl sulfide in significant quantities. The chemistry is not quite right. Volcanic sulfur on Earth tends to come out as inorganic compounds, which then react with seawater and biology to produce more complex molecules. Without biology, the chain stops at the inorganic stage. Volcanic dimethyl sulfide, if it exists, is rare and short-lived, but K2-18b is not Earth. Its conditions are different, and its hydrothermal systems, if they exist, would operate under far higher pressures and possibly different temperature regimes. Some researchers have proposed that under exotic conditions, perhaps in superheated water rich in dissolved hydrogen, abiotic synthesis pathways could produce small amounts of dimethyl sulfide directly from inorganic precursors. The chemistry is speculative. Laboratory experiments have not yet demonstrated such pathways at the rates needed to match Webb's observations, but the possibility cannot be entirely dismissed. There is also the question of how dimethyl sulfide produced at the seafloor could reach the upper atmosphere where Webb detects it. On Earth, deep-sea volcanic emissions rarely make it to the surface in significant quantities. Most are absorbed by seawater or oxidized along the way. On K2-18b, with potentially hundreds of miles of ocean separating any volcanic source from the atmosphere, the same problem would apply. Unless production rates were extraordinarily high, abiotic dimethyl sulfide from volcanism would be expected to remain trapped in the deep ocean rather than venting into the air. This is where the volcanic hypothesis runs into difficulty. Even if volcanic chemistry could produce some dimethyl sulfide, getting it from the seafloor to the atmosphere at the abundance observed would require an unusual mechanism. Strong vertical mixing currents could, in principle, carry the gas upward, but the transport timescales would still favor breakdown along the way. The molecule is fragile. It does not survive long in the presence of oxidants or ultraviolet radiation, both of which exist in abundance higher up in the atmosphere. Biology, by contrast, has no transport problem. Phytoplankton on Earth live in the upper ocean, where their sulfur emissions enter the atmosphere directly, with minimal travel through water. If life exists in the upper layers of K2-18b's ocean, The dimethyl sulfide they produce would reach the atmosphere efficiently, in concentrations consistent with observations. The volcanic hypothesis is not impossible. It is, however, a stretch. Each step of the proposed mechanism faces challenges that biology resolves naturally. The simplest explanation, the one that requires fewest unknown processes, remains the biological one. But simplicity is not proof. There is one more place to look for life, a place darker than any sea Earth has ever known. If the upper layers of K2-18b's ocean turn out to be too hostile, too pressurized, or too irradiated for life as we understand it, biology might still exist somewhere else on the planet. The deep ocean. Earth has shown us, repeatedly, that life can thrive in places without sunlight, drawing energy not from photosynthesis but from chemistry. Hydrothermal vents on the Earth's seafloor host entire ecosystems that have never seen the sun, fueled by minerals and heat rising from below. The discovery of these ecosystems in the late 20th century rewrote what scientists thought possible. Before then, the prevailing assumption was that all life on Earth depended, ultimately, on solar energy. Plants converted sunlight into food, animals ate the plants, and the food chain extended outward from there. The vent ecosystems shattered the rule. They are powered by chemosynthesis, in which microbes extract energy from compounds like hydrogen sulfide that rise from the planet's interior. Tube worms, vent shrimp, and entire microbial mats live around the vents, building food webs that have no connection to the surface biosphere at all. If K2-18b has a rocky core and an ocean, it almost certainly has hydrothermal activity at the seafloor. Where there is heat and water and rock, there is chemistry. The deep sea of K2-18b might host its own version of vent ecosystems, organisms that draw energy from thermal and chemical gradients, rather than from the dim red light of K2-18 above. The catch is that life of this kind, even if it exists, would be very difficult to detect. Chemosynthetic organisms in the deep ocean produce their own characteristic chemical signatures, but those signatures would be locked in the seafloor. Getting them into the atmosphere where Webb could see them would require strong vertical mixing, or, more likely, a connection between the deep biosphere and the surface waters. On Earth, the deep biosphere does contribute trace gases to the atmosphere, but the contribution is small compared to surface biology. Still, the existence of even a deep biosphere on K2-18b would be a profound discovery. It would mean that life is not just a surface phenomenon driven by photosynthesis. It would be a deeper, more universal feature of any planet with the right combination of water, energy, and rock. The implications for the prevalence of life across the galaxy would be staggering, since deep biospheres would be possible on a much wider range of worlds than surface biospheres alone. Some researchers have suggested that K2-18b's atmospheric dimethyl sulfide signal could, in principle, come from a combination of surface biology and deep-sea contributions, with the chemistry mixing through the ocean column over time. The exact balance depends on details we cannot yet measure, but the presence of multiple potential sources, all biological in origin, makes the signal more robust to objections about any single mechanism. Earth's vent ecosystems also offer a clue about how life might begin. Many origin of life theories propose that the first organisms on Earth emerged near hydrothermal vents, where chemical gradients provided the energy and the building blocks needed for the first biochemistry. If the same is true on K2-18b, the planet might host life that originated billions of years ago around its own seafloor vents and has been evolving in its peculiar environment ever since. That alien biology, if it exists, would be unlike anything we have ever encountered, and whether we ever truly understand it depends on telescopes that are still being built. Suppose, for a moment, that the next round of Webb observations crosses the 5 sigma threshold. Suppose the dimethyl sulfide signal holds up the abundance estimate stays high, and every plausible, non-biological explanation is systematically ruled out. Suppose the scientific community, after years of debate, converges on a consensus that K218b is, in fact, host to some form of life. What changes? The immediate impact would be philosophical. The question of whether life exists beyond Earth has hung over human civilization for thousands of years. Every culture has wondered about it. Every religion has touched on it in some form. The shift from wondering to knowing would be one of the most profound moments in the history of human thought. It would not answer every question, but it would close one of the oldest open ones. We are not alone. The scientific impact would be enormous. Astrobiology, currently a small and somewhat speculative field, would become one of the central disciplines of 21st century science. Funding for biosignature research would increase dramatically. Future telescopes would be prioritized for follow-up observations. New mission concepts, including direct imaging of K218b with extremely large space telescopes, would be proposed and funded. The entire infrastructure of exoplanet research would orient itself around the central goal of understanding the alien biosphere we had just confirmed. Religiously and culturally, the consequences would be more varied. Different traditions have prepared for the discovery of extraterrestrial life in different ways. Some have doctrinal frameworks that easily accommodate it. Others would face significant theological reinterpretation. The history of human thought suggests that, in the long run, religious traditions would adapt. The shorter term might involve some turbulence. For the broader public, the news would be initially electric and then, perhaps surprisingly, settle into something more mundane. The life on K218b, if confirmed, would be microbial. It would not communicate with us. It would not visit us. It would not threaten us or assist us. It would simply exist 124 light-years away, doing whatever it does in its alien ocean. People would absorb the news, marvel at it, and then return to their daily lives. The discovery would become part of the cultural background, taken for granted within a generation, the way the existence of other galaxies became taken for granted in the 20th century. The deeper implication runs beneath all of this. If K218b has life, the universe is not stingy with biology. The Milky Way contains billions of habitable zone planets. If even a small fraction of them are alive, the total number of biospheres in our galaxy alone would be in the millions or billions. Life would be common. The question would shift from whether life exists elsewhere to how often, in what forms, and under what conditions it arises. That shift would feed directly into the search for intelligent life. Microbial biospheres do not by themselves imply civilizations, but they raise the probability. If simple life is common, complex life might also be common, given enough time and the right conditions. The galaxy could be teeming with biology of various levels, including some that has developed technology. The Drake equation, which estimates the number of communicating civilizations in the Milky Way, would suddenly have its first observational input. Real numbers, not pure speculation. That equation has been waiting for over 60 years. K218b might finally start filling in its variables. In 1961, the radio astronomer Frank Drake wrote down a simple-looking equation on a chalkboard at a meeting in Green Bank, West Virginia. The equation was an attempt to estimate the number of communicating civilizations in the Milky Way galaxy. It multiplied 7 factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction on which life actually arises, the fraction of those where intelligence develops, the fraction of intelligent species that produce detectable signals, the length of time those signals last. For more than half a century, every term in the Drake equation, except the first, has been almost pure speculation. The rate of star formation is well measured. Everything else has been guesswork, with estimates spanning many orders of magnitude. The total number of communicating civilizations in our galaxy could be 1. It could be 1,000,000. Different reasonable assumptions produce wildly different answers. K2-18b, if confirmed as a host of biological activity, would change the equation in a fundamental way. The third term, the number of planets per star that could support life, has already been refined by exoplanet surveys to suggest that habitable zone planets are common, possibly orbiting most stars. The fourth term, the fraction on which life actually arises, has been the great unknown. With one confirmed biosphere beyond Earth, that fraction would be measurable for the first time. Even a single detection produces a rough estimate. If K2-18b is confirmed as alive, and if comparable surveys turn up other Hycean candidates with similar chemical signatures, the fraction of habitable zone planets that host life could be on the order of 1 in 10, or 1 in 100, or 1 in 1,000. Even the lowest of those estimates would imply that the Milky Way contains tens of millions of biospheres. The question of whether life is rare or common would tilt firmly toward common. Of course, microbial life and intelligent life are very different things. The Drake equation's later terms, dealing with the fraction of biospheres that produce intelligent species, remain essentially unconstrained. K2-18b would not give us direct information about intelligence, but it would push against one of the most pessimistic versions of the equation, the so-called rare Earth hypothesis, which holds that the conditions for life are so specific that Earth might be the only living planet in the galaxy. If K2-18b has life, Earth is not unique. The rare Earth hypothesis weakens dramatically. Other habitable zone worlds, by extension, become candidates for biology in their own right. The galaxy starts to look less lonely. Whether or not any of those other worlds host intelligence is a separate question, but the foundation for the entire search shifts. We would no longer be looking for the second case of life. We would be looking for the third, the fourth, the 100th. The implications for the search for extraterrestrial intelligence, often called SETI, would also be substantial. SETI surveys have been running for decades, scanning the radio spectrum for artificial signals from other civilizations. So far, they have detected nothing. The result is consistent with no civilizations existing nearby, but it is also consistent with civilizations existing but being too quiet, too distant, or too short-lived to detect. A confirmed biosphere on K2-18b would not change SETI's null result, but it would strengthen the case for continuing and expanding the search. If life is common, civilizations might be common too. We just have to keep listening. The next decade of exoplanet observations will tell us more. The K2-18b story is unfinished. As this script is being written, the data from the initial Webb observations is publicly available, and multiple teams around the world are running independent analyses. Some are reaching conclusions consistent with the Cambridge team's biosignature interpretation. Others are finding that the data, under different modeling assumptions, does not require any specific molecule beyond the confirmed methane and carbon dioxide. The debate is active, ongoing, and unlikely to be resolved before the next round of telescope observations. The path forward is reasonably clear. The Cambridge team and others have applied for additional Webb time to observe more transits of K2-18b. If approved, those observations will likely take place over the next year or two. The new data will be combined with the existing data, and the statistical confidence on any biosignature signal will rise or fall accordingly. If the signal holds, the field will move toward acceptance. If it weakens, the K2-18b biosignature claim will join the previous near misses in the history of the search for life beyond Earth. Beyond Webb, the next generation of telescopes is already taking shape. The Habitable Worlds Observatory, the Extremely Large Telescope, and other major projects will provide the tools needed to either confirm or rule out biological activity on K2-18b with much higher confidence. The full picture will not come from any single observation. It will come from an accumulation of measurements, taken over years and decades, that together build an undeniable case in one direction or the other. In the meantime, the search broadens. Other Haitian candidates are being characterized. Other types of potentially habitable worlds are being added to the target lists. Earth-like rocky planets in the habitable zones of sun-like stars remain the long-term goal, since they offer the closest analog to our own world. The current generation of telescopes can study them only with great difficulty. Future telescopes will be optimized for exactly that task. The honest answer to when we will know whether life exists on K2-18b is sometime in the next decade. By the early to mid-2030s, with additional Webb time and the first results from new ground-based telescopes, the case should be much sharper than it is today. By the 2040s, when the Habitable Worlds Observatory becomes operational, the question should be much closer to a definitive answer. And by the 2050s and beyond, the search for life beyond Earth will have matured into a systematic survey of dozens or hundreds of candidate worlds, with statistical results rather than single-target debates. For now, K2-18b sits at the frontier. It is the planet that pushed the field across an important threshold. Whatever the truth turns out to be, the very fact that we are having this conversation, debating in scientific journals whether a specific molecule on a specific exoplanet does or does not indicate life, represents a milestone. A century ago, exoplanets were a theoretical concept. 50 years ago, the first ones had not yet been discovered. Today, we are reading the chemistry of their atmospheres and arguing about whether those atmospheres host living organisms. The progression is breathtaking when you step back and look at it. The story of K2-18b is the story of humanity learning to read distant worlds. It is messy, contested, and incomplete. It is exactly what early discovery looks like. The light from the planet keeps arriving, the instruments keep listening, and somewhere, 124 light-years away, an alien ocean continues its silent rhythm, indifferent to our debates, breathing whatever it breathes into a sky we can only imagine. Eventually, we will know. Until then, we keep watching.